All right. Welcome to the second Bioinformatics and Computational Biology seminar this semester. Today we have Dr. Olexandr Isayev from Carnegie Mellon University from chemistry. I met Olexandr, I think last semester when virtually, when I had a chance to give a seminar at computational biology in CMU. And I was very impressed that he is applying now deep learning for very fundamental like equation for Schrodinger's equation for which can be accelerate the like physics actually, not just only for drug discovery, but very going to fundamental. Then now, he's going to apply for drug discovery. So Olexandr is got PhD in 2008 in computational chemistry, and then he did postdoc at Case Western Reserve University, and then also was a scientist at the government research lab, and he was faculty at UNC Eshelman School of Pharmacy of the University of North Carolina at Chapel Hill from 2016 to 2019. Recently, he received Emerging Technology Award from the American Chemical Society, and also NVIDIA supports him with the GPU Computation Award. And so today he will be talking about really the state-of-the-art application of deep learning. Now deep learning is going everywhere, but now going to really the physics, which is really fundamental and exciting. His title of the talk of the title is Accelerating Drug Discovery with Machine Learning and AI. Dr. Isayev, please.
Okay, thank you so much. And thank you so much for the invitation. And I apologize, there is my little helper who wants to sit in front of the computer. So today I'd like to talk about some of our work, how we use deep learning and neural network to accelerate quantum mechanics. And don't worry, I will not going to show you, the derivation of, large equations, but rather, how these technologies can be applied, to challenging problems in chemistry, in particular, drug discovery. Before I run out of time, let me acknowledge a lot of people who can contribute to these projects, foremost members of my lab, collaboration with my good friend and partner in crime, Adrian Roybig from University of Florida, Maria Kurnikova here at CMU, also some industrial partners and companies like Inamin, who synthesize compounds for us, funding from NSF and ONR, and a lot of various agencies and providers of HPC resources, because training some of these things and obtaining reference data is really computationally expensive. Now, let me start with the motivation. You've probably seen AI and, all this kind of hype is all-time high. And even if you look in the news from the, a scientific organization. So there is the news outlets from the Royal Society of Chemistry, and it's wanted synthetic chemist, humans need not apply. Or there is a chemical engineering news, rise with the smartish machines, and list can go on and on. So I'd like to start, kind of with the interesting motivation quote. And and it's attributed to Derek Lowe, who's writing the blog for the Science Translational Medicine. It is not that machines are going to replace chemists. It is the chemists who use machines will replace those that don't. So I think it's an interesting thought-provoking quote, especially from Derek, who's very, who's a pharmaceutical industry veteran and typically very skeptical about, many of these hype things. So I thought it's an interesting motivational quote. Now, if you look for, kind of a motivation that, drug discovery is hard. You probably have seen, cartoon like that many, many times. It's slow, it's expensive, when the gene and target been identified, the actual process, in chemistry can take 5-7 years, and we typically, depicted as the funnel, when you start from, computational screening and then experimental high throughput screening. So thousand compounds been sifted through, maybe hundreds of leads identified, and you go to a lead optimization, and ending up with the, 1 or 3 compounds just to fail somewhere in the clinical and, trials, things like that. So very expensive, very slow. And, even in this emergent situation, what we see right now with the COVID, if you've seen, the vaccines were developed, but so far, no FDA approved drug, no new drug been developed. Because even under this emergency situation, this is a very, very hard problem. So machine learning and generally data sciences actually do apply it all across this pipeline. And kind of the mantra being, we always aim for success, but if we fail, I would like fail early and fail cheap. So instead of running hundreds or thousands of compounds, so maybe some of this technology help us to, maybe run 10% of these experiments and save money and time. So in my lab, we apply, as a computational chemistry lab, we don't do any with, bench chemistry things. Across the pipeline, we work in several areas. And as I'll show you, so we use AI and machine learning accelerated physics simulations. For example, you can assist in molecular dynamics simulation and finding a 3-dimensional structure of molecules. We do work with medicinal chemists, and we use some of the machine learning to do computational screening for a particular projects. And internally, we develop a libraries of on the order of 10 billions of molecules, which corresponds to most of the commercially accessible chemical space. And we've done some pipelines. Basically, you can screen 10 billion molecules within a couple of days. So it's very, very rapid screening using machine learning methods. We're also interested in generative chemistry. This is really fascinating subject when the machine can take on human and take this creative component and can essentially dream molecules and suggest you, in my case, on molecules. But you probably have seen examples, fake pictures and videos, things like that. And also, there are some place where machine learning can be applied for toxicity and off-target effects. So in my talk today, I primarily want to focus on these 2 boxes on the left. Let me start about the need for the generative model. One of the problem why drug discovery is hard is follows. Right now, for essentially 200 years of modern chemistry, and mostly by efforts in companies. So the biggest commercial database of molecules on the order of 10 to the 9 compounds. However, if you look for, you can combinatorial estimate number of the chemical space or number of possible organic molecules that can be out there. And there are various numbers. So the most popular is 10 to the 60. And 10 to the 60 is unimaginably large number. This is more than atoms in the universe, and this is so big we cannot comprehend how large it is, and therefore, you see this is a huge gap between what we know and what might be out there, and therefore, when you do a drug discovery and applies a screening technology, so you screen this billion molecules, essentially you screen what's shown in this cartoon. You just look under the lamp, kind of ignoring all the space out there, which we don't know. And therefore, all the current databases have this observational bias. And therefore, I think there is an interesting opportunity where machines can help us to, extend the boundaries of chemistry. Now, and my dream as the computational chemist would be something like that. When we can ask a smart machine to essentially do this, what's in industry called DMTA cycle. So you predict, synthesize, measure, and repeat, and all this driven by, for example, an algorithms. So you task a machine to develop a molecule or material for specific tasks, think a little bit and give you a hypothesis, a molecule, and maybe a recipe how to synthesize. Then this recipe is executed. And for example, a robotic platform can synthesize a molecule, send it to biological screens, and receive a feedback. If the model was wrong, molecule is inactive or insoluble or something like that. Basically, you can learn from this mistake and basically repeat. So that would be a dream. And so essentially, you have AI-driven molecular discovery. And this process is hard, and many labs in many countries work on that. And I kind of think about this problem as we solve this one Lego block at a time, but building a tower. And in my lab, we work on a couple of computational blocks, mostly in this corner. But there are many experimental labs who actually push the boundary of robotic systems and high throughput experiments as well. Now, if you've seen, in machine learning, you're probably familiar with what a predictive model are. And, let me show you a quick example to contrast what a predictive and generative models are. Imagine you have X, and apologies for, it's a little bit scrambled form. So imagine you have X would be your sample. In my case, those are molecules. And Y would be some kind of numeric property. In our case, it's typically biological activity, maybe solubility, things like that. So when you do normal predictive models, things like regression classification, essentially you explore this, a probability distribution function of Y given X, labels given my samples. In other words, you take molecules, and you embed them in some kind of high dimensional space, and then you predict the properties. And then you look one molecule or a bunch of molecules at a time and look the molecules that might have variable properties. So generative models is inverted. So in chemical and material sciences, it's also known as the problem of inverse design. So you look for the probability distribution function of X given Y, so it's flipped. And therefore you start from desired properties, you embed it in some kind of high dimensional space, and then you start from the point of the desired properties, and then they look for the molecules that corresponds to these properties. So you flip the problem. So essentially you invert it. Now, you probably have seen, so the illustrative example would be, these generative models of pictures. You've seen pictures of dogs, cats, the face generation, the fake new videos, all that as examples. Basically, you learn the probability, the distribution of images, for example, what corresponds to a dog's, and then you can sample and then generate new images of dogs. So you probably have seen it all over the news. Now, so the relevant examples would be very similar, but instead of generating pictures of cats and dogs, we want to generate structures of molecules. And there are numbers of ways to do this, because obviously molecules are not images. And one of the way why the generative models are especially interesting, because we can combine it with another technology, it's called reinforcement learning. And you probably have seen system like AlphaGo that play game. For example, it won the world competition playing the game of Go, and game of Go is the most complex board game what we have. And very briefly, so in reinforcement learning, so you have some kind of AI agents that doing some action, and in case of a game of Go, it moves checkers on your board, and then it interacts with the world. In this case, with that player, and basically receive position of the checkers on the board and the reward. And basically playing the game, you do one movement at a time. And your reward, ultimate reward, would be you lose or win the game, right? So we were inspired by that concept. Now imagine that I have my neural network, and I'll tell you on the next slide exactly what kind of neural network we use. Instead of moving checkers, let's draw atoms and draw chemical bonds. and play a molecular game of designing a molecule. And in our game, instead of winning or losing, we will use a proxy, essentially an oracle. It may be another neural network that predicts some useful properties. In our case, that can be, solubility, binding to a protein. It can be any useful feedback. For example, we can predict IC50 binding, half inhibition of particular enzyme, things like that. In principle, this part can be very flexible. That can be physics-based simulation. That can be real high-throughput experiment. But for sake of time and exercise, we use a proxy machine learning model. And then our game would be, so generative neural network, draw a molecule, feed it to a predictive model, and this model, depending on specific task, give us reward of computing the properties and estimating, are these properties good or bad? And we close this loop and have a feedback to inform the neural network how good or bad these molecules are. Now, again, as I told you, molecules are not images, and therefore we need a special way how to represent the molecules. And there are several ways that have been developed. Most of the early works were used what's called the smile strings, and they use string-based method. So if you work in bioinformatics, you're probably familiar with like a sequence of protein. That would be a string representation of the protein. In our case, there is an algorithm that you take a molecule and basically traverse a graph and generate a special sequence that encode the structure of the molecules, and it looks like this. So essentially, it's a sequence of characters. However, a more natural approach for molecules would be a graph. Because molecules, they do indeed looks like a graph because we have our nodes that would be our atoms, and nodes are connected through edges. Those are chemical bonds. And even more relevant representation, that would be three-dimensional conformers. We published a couple of papers, so we developed a couple of methods how to use strings, how to use graphs, and we currently work in the three-dimensional representation, which is more, arguably hardest to do. But you can use one of these methods. And now again, back to the sequence. So this what we call language of smiles or smile strings. It's essentially an algorithm that take these molecules, make it look for cycles. It cuts the cycles by algorithms, built in a tree, and basically in a specially described way, basically map this essentially a tree to a sequence, and you get the structure of the molecules. Now, what we can do, we can now learn from field of text mining and languages. So we can use recurrent neural network, and now we can learn the probability of characters in our essentially new language of smiles, right? So you think about, you can take recurrent neural network, and you start initiation the sequence and learn how to predict next sequence given the previous one. Standard application of recurrent neural network. In our case, we thought that the descriptive capacity of current recurrent neural network is not enough. So we use a little bit more sophisticated, what we call stack augmented recurrent neural network. And those are one of the flavors of the neural Turing machines. And if somebody interested, there are some theoretical reasons why this particular architecture better for learning language of smiles. Nevertheless, when you train in inference mode, essentially you start from this start token, and your neural network predict first, string, first character in the string, then you pass its embedding to the next one, and basically you generate sequence of characters. And at the end, when modern model decides, it terminates molecule with the end token, and you generate a new molecule. So this is how a sequence model works. In terms of graphs, again, molecules are graphs. So this is my favorite molecule of caffeine, for example. And in that case, we come up with a slightly different architecture, which we called a molecular RNN. And here is the preprint. But very quickly, so we initialize a molecule, always start from an atom, And then we have two separate neural networks. One is the atom generating network and the bond generating network. And therefore, we do after aggressively generate, after first atom, we generate, second atom and then predicts if it's connected or not. So in this case, there's only one possibility. Second atom can be connected, only the first one, right? So we predict that, that it's connected. And then when we generate one, the third atom, then we have possibilities that this third atom might be connected to a previous one and one before it, right? So we predict, yes, this atom connect to this one with double bond, so it has two bonds, and not connected with the one before, and so forth. So you essentially roll it, and then atom generation stops when the next atom is predicted not to be connected to anything else. So that completes our molecule, and we have the graph. And now just a little bit quickly for those who are interested, how we use our predictive models. So it's essentially, you can think about normal machine learning models built on historical data. In our case, we use kinase proteins. And our lab participated in this NIH-sponsored challenge to predict essentially binding affinities for many kinase proteins, and we use machine learning, and our lab was one of the winners of this challenge. So again, it's just machine learning model. Now let's combine all of this together. So now we have generative model. It generates our sequence of smiles or a graph. There's our molecule. We feed it. There is our predictive model. And it says, oh, I'm an active. Then we use our reinforcement learning. In particular, we use what's called policy gradient algorithm. So here's my stick. And basically, we modify the weights in the direction to improve predicted activity. And basically, you loop, you iterate. Now there is my second molecule. Now it's going to predict it as active. Here is my carrot. And again, we use reinforcement learning, and you iterate until you train the system. And after that, the model starts to learn what means to generate this particular active molecules. And so visually, what looks, it's a small kind of animations. So when you start initiate this exercise, basically this is the probability of the molecule being active at a certain particular cutoff of activities. When you initialize it, it's all molecules essentially being generated as inactive. You run this exercise, and the reinforcement learning start to shift this distribution into the right. So more and more molecules are being generated as predictive to be active. Now, we've done a couple of validation for these methods. So for example, we team up with the Structural Genomic Consortium to work on some of the kinase inhibitors. And we run this exercise for CDK2 protein. And I just show you one example, not to bore you with big tables. In particular, we come up with particular molecule, we send it to enamine, synthesized, then tested. So we found some, semi-decently active molecules, so 300 nanomolar activity against CDK2, been verified. And we thought it's a new scaffold. But then when we dig deeper into literature, as usual, there is something been already done. Unfortunately, we found this is it's a known chemotype for CDK2. There is a JMedChem paper, which has very similar scaffolds. So unfortunately, that particular scaffold been described. But the good thing that in our training data, this was not part of it. So that's kind of our reinvention of the new active molecule. But nevertheless, it's an example that you can do useful too. We also apply it for a couple of other examples. There is another example that we used with graphs. We wanted to maximize a melting temperature, predicted melting temperature. So you start with the generative model, and this is your distribution of melting temperature, which is the typical medicinal chemistry range. When you run maximization, you shift the distribution extremely on the right. And then when you look for this high melting temperature molecules, you look something like that. And to me as a chemist, totally makes sense. So fused aromatic rings and these heteroatoms do indeed increase a melting temperature. So it again makes totally chemical and physical sense. Now with that, all of our code are typically open, and my students implement all of these methods in our package, which we called OpenChem. So it's a modular, very user-friendly, scientist-friendly framework built on top of PyTorch. So it implements variety of different tasks, different types of predictors and coders, different types of layers. We get some data sets. You read sequences, things like SMILE, FASTA, and molecules. We can do classification, regression, multitask, generative models, reinforcement learning, and some supportive tools to work with molecules, data processing, tokenization, things like that. And the beauty of that, it's all in PyTorch. And basically, if you work in PyTorch ecosystem, you can mix and match because all objects are PyTorch native, and you can use any library in PyTorch. So if you're interested, there is a paper on GCM just published last month, and it's on GitHub. There's a link. Again, give it a try, and let us know if it works for you. Now let me switch gear for a little bit. I talked about generative models. Now let's talk about some other Lego piece is in the predictive side. So when we do the virtual screening, and especially when you do computational, what we call the virtual screening, on this very early stage, when we screen libraries of molecules, one of the approach, for example, what we would call the structure-based drug discovery methods, where you're looking to understand the interaction between ligand and the protein. And it's typically done either from docking, when you dock a molecule into active site of the protein, or molecular dynamics, when we look for time evolution of protein ligand complexes. And the choice of the methods to study this interaction would be called molecular mechanics, or what's called the force fields. And there's an extremely simple model where bonds, essentially balls, hard spheres, connected with springs as chemical bonds. So essentially it's a balls and springs, very simple, kind of a Newton's mechanics of model. And overall potential is actually, some of this, very simple laws, for bonds, for angles, and angles that would be 3 atoms, and torsion dihedral would be sequence of 4 atoms, and also what's called non-bonding terms, things like van der Waals interactions and solvents effect. So it's a very simple analytical function, but nevertheless, you have to fit it based on known physics, biology, and chemistry to reproduce some of the experimental observables. And there's like many years, like 50 years of history fitting these potentials to describe dynamics of proteins. Now, the problem is that molecules are not simple balls and strings. Molecules are quantum objects, and they, in principle, have to be described by the Schrodinger equation, the behavior of the quantum mechanics. This is an example. This is what's called time-independent Schrodinger equation, and it's a partial differential equation, and it's solved numerically. And this is, since there is no analytical solution for anything practical, we use big supercomputers to use numeric approximation and to justify these machines. However, if you look at this equation from point of view of machine learning, you can rearrange this quantum complex equation as our great state energy would be a magic function f of the molecular input coordinates of my atoms. And this is a regression problem. And the magic function f, that would be our machine learning models that seeks given our input feature predict in our case energies, right? This is exactly what we do. Take molecules, feed them through a neural network, predict energies. And the great thing about the neural network, they're differentiable, so we can backpropagate and we can get gradients and therefore forces on on every atom. And therefore we can do dynamics, we can do all kind of simulations. We can also have second derivatives as well. So we can compute Hessians and all other things. And therefore, I think the promise of the machine learning methods is the following, is that in this cartoonish representation, that if you want to study realistic systems, you confine to this corner when we use the simple force field methods. But they come with you pay the price that simple form may be lots of error. And in order to rigorously improve the quality of the predictions, you used to include the quantum mechanics. And therefore you pay extreme price of this scaling, computational scaling, because some of the more expensive methods scale, for example, at N7. And this is not the most expensive method. Nevertheless, you can never compute proteins with these methods. They're typically accessible to molecules, size of 10 atoms or so, very small system. And therefore, I think the value of the machine learning methods is to combine the speeds, because neural networks are almost linear scale to data. And if we use a particular approximation of quantum mechanics, we can approach its accuracy. This is essentially our work. And over the years, we developed a number of different methods and complexity of molecules. I will not go into deep technical details, but we started with kind of a simple feed-forward neural networks, and we can include various skip connections and residual connections. And finally, that's just one example on the right, where we can combine neural network and a simple Hamiltonian and essentially make a hybrid of machine learning and physics-based methods. And in my opinion, this is one of the very promising directions in the future, where we combine physics equation plus machine learning. Let me start with just show you one example of what we called ANI, deep neural network. And to my knowledge, it was one of the first methods where you can train this neural network and apply it to a wide variety of classes of organic molecules. So the methodological foundation, this chemical science paper 2017. But very briefly, we use an idea that chemistry is semi-local. And therefore, you don't need to describe full molecule to describe the interaction of the specific atom. Therefore, we use the idea of molecular representation as atom-centered environment, where each atom is characterized by a sphere around it of certain radii. In our case, so this is the diameter of the sphere, about 1 nanometer. And you encode all the atoms and all the parts of the molecule in this sphere in terms of what we call radial and angular distribution functions. And therefore you have like a fingerprint that encodes this atomic environment. So your neural network essentially zoom in one environment at a time at each of this molecular atomic neighborhood, and the total energy of the system would be sum of this essentially atomic neighborhoods. So then again, you pick your favorite framework, you compute a particular approximation of quantum mechanics. For every molecule, you featureize, compute these descriptors, pass through neural network, computes these atomic environments, sum them up, and then look for errors from ground through essentially a quantum mechanical answer, compute coarse gradients, update the weights of neural network, and basically iterate. So standard neural network training. At this point, we parameterize 7 elements from the periodic table, but those are mostly useful. So those are biogenic elements, most useful in biology. So carbon, hydrogen, nitrogen, oxygen, sulfur, fluorine, chlorine. We work on more elements. If there are any computational chemists in the audience, so there's a bunch of acronyms with the particular flavor approximation of the we use density functional theories with the particular types of quantum mechanical calculations. But for this purpose of the talk, details are not very important. Now, what it can give us is very accurate description of potential energy surface, energy and forces for molecules. So for a very wide window of energies. We can give an accuracy from 1 to 2 kcal per mole in terms of energies, relative energies. And on the right, again, this is one of the examples where the traditional force fields have hard time to describe is the essentially changes in energy depending on these dihedral angles. So if I take this two, and there's a bunch of different molecules, if I take pairs of dihedral angles, I can build this two-dimensional in this two dihedral angles maps of energies depending when I change the dihedral angles. So on the left, that would be our approximate neural network. On the right, that would be ground state DFT. And in many cases, basically, you can hardly see the difference. And so the neural network can describe even this, kind of the smallest kinks and kind of feature of this potential energy surface. This is exactly what needed for accurate description of the behavior and the dynamics of the molecules. The cool thing, you can use a learned representation from this neural network, do kind of chemical insight, and for example, you can do embeddings and look for what neural network learn. And for chemists, it's really exciting because, for example, all atoms are clustered together and kind of resembles a little bit on, piece of the periodic table. But when you look into, position of these embeddings, for example, carbon atoms, kind of you zoom in and you can see all the carbons that have particular substituents are clustered together. So it totally makes chemical sense. So you can monitor these chemical changes during your simulation and have a little bit of chemical insight from this chemical features. Again, one of the applications, for example, we can use this method to predict also outcomes of chemical reactions. We have this preprint recently. What is most important, so for example, we have a certain chemical reactions and we're interested in what's called regioselectivity, where the substitution of this reaction occurs. And what is, I'd like to draw your attention, to this table here. So if I use a particular type of quantum mechanical calculations, I get certain types of accuracy. If I combine two, and I can improve a little bit and basically approach to a 90% accuracy. However, I pay the extreme price of this computation. And out of the box, basically, if you use some of these features that neural network provides, this learned embeddings, you can essentially approach the same accuracy, but 1,000,000 times faster. This is really transformative for the way accessibility and democratization of these calculations, because now you can do this calculation on laptop instead of running supercomputer facilities. And just to show you show off a quick movie. So what you see here is the simulation of 4,000 carbon atoms. It's a hot carbon vapor, essentially 2,500 kelvins, and we run molecular dynamics simulations. High temperature, several nanoseconds. What you can see, random vapors start to condensate. You see the nucleation and formation of carbon nanoflakes. You also see formation, you see this is a buckyball, this is a fullerene. And then this carbon material start to grow. And you can see formation of nanotubes, things like that. And again, this shows you that, we can describe realistic materials, and, again, tremendous benefit of speed ups versus quantum mechanical calculations needed to do it otherwise. Now, let's back to, kind of more relevant example in biology. What we work right now is extending our framework from molecules to proteins. And this work is currently under development, but let me show you a quick movie. Essentially, it's a development neural network that runs dynamics of this particular ligand and protein complex. We've done simulation in box of water, stable, and, looks good. So we hope to soon, have these possibilities to run these dynamics. And where this simulation would be useful is we think at least in two ways. One, we can assist in refinement of crystal structures for proteins. For example, if you do cryo-EM or X-ray crystallography, I'm not crystallographer, but so the pipeline crystal structure refinement is extremely complex. You start from either images, do data processing, but this very last step is the model refinement. And my understanding is that some of the to do it very high accuracy crystal structure to atomic resolution, they run quantum mechanical simulation and fit to the density and essentially reconstruct the crystal structure. So that might take for large systems days and even week using small HPC cluster or GPUs. And this is where we think we can plug in. So we work with team of Phoenix, who were one of the developers of the software for the crystal structure refinement. So you can replace the quantum mechanical aspect with the neural network and essentially take the crystal structure refinement down to minutes on a laptop. Again, given I have a GPU. So stay tuned for that. But meanwhile, already we can see what we can do it now. So go back to the question where we want to understand the binding of the ligand to a protein. And typical state of the art for the protein ligand binding is the accuracy 1 to 2 kcal per mole for very well behaved systems. And not all proteins are very well behaved. Some of the parameters for the force fields give a lot of physical results, and sometimes you need to refit this parameter, so it's often a mess. So here's what we did. So there is a benchmark data set that have very high accuracy experiment of protein ligand binding. So this particular protein is again kinase called TYK2. And this is not very well behaved system. Despite the fact that kinase is one of the most popular family of the proteins, there's a congeneric series of this molecule. So this is our kind of a molecular core and bunch of substituents as this R. And those are high quality binding free energy, essentially binding affinity measured by the experiment. So when you do state-of-the-art simulations, you will get accuracy, something like that. So diagonal would be a perfect fit. So this experimental free energy, computed free energy. If you can use in terms of the errors, kind of summary statistics. So root mean square error, 1 kcal per mole of energy. However, look for R square, it's 0.4. So this ranking is actually screwed because we have this lots of ugly outliers. And if you look for, especially in the lead optimization, you always look for ranking and maximal improvement. So for many industrial applications, this is not acceptable. But this is the fact, what is the best computational methods can give us today. So I team up with a group of John Cadera from Memorial Sloan Kettering. And one of his students come up with this clever trick. When you run this simulation, you can combine, you can simulate a ligand with our force field, and the rest would be a still, classical force field. So in a sense, you do a hybrid simulation, but the ligand would be simulated with our neural network and see what's going on. Long story short, if you're interested in technical sites, there is a preprint paper still under review. Basically, to do this, what we use an approach was called alchemical free energy calculations. And to do so, you put a free energy cycle, and one ligand and another ligand, and do clever transformation. Then you do simulation, and you compute free energy from this, and from these energy cycles. So we can augment this free thermodynamic cycle with this hybrid simulation using a neural network, and run it and see the correction what the neural network makes on top of the simulation with normal force field. And here is what we get. So this is the correction for this all congeneric series. And this is its value. Sometimes it's small, but it can be as large as 4 kcal per mole. So it can be very large. And if you look for relative free energy difference, therefore difference between, for example, that and that, or that and that, this is what you get for the force field, accuracy 1.2. And basically this is what you get with the neural network. This is the delta free energy. But in the grand theme of grand scheme of things, for the absolute binding free energy, this is what we started with our outlier, and this is what you're getting. It's amazing that, you know, we reduce error by 50% from essentially 1 to a half. But the R square, again, double from 0.4 to 0.86. And therefore, essentially all the ligands are within acceptable error bar. We drastically improve the ranking for the free energy. And it comes with essentially very limited, you know, overhead for computational expenses. It's all implemented in our codes. And just to give you an idea why it works. So this is a picture from another paper, but it uses, again, our neural network. So this is another you know, protein ligand interactions. But let me show an example. If you do the simulation with the standard, you know, proteins, this is kind of potential energy surface you get. If you believe the quantum mechanics gives you a right answer, so that would be almost exact answer because of very high level of quantum mechanics you use. As you can see here, they have nothing in between. They are absolutely different. And this is what, you know, is our neural potential gives you. So it's very close approximation. In many cases, you cannot see the difference. And if you look for a most, you know, favorable conformation of a molecule inside the active site of this pocket of this protein, so the green, that would be what force field wanna give us. The blue would be X-ray, and this kind of dark red, that would our neural network potential would give us. So actually very, very close match with exception of this, you know, tails groups. With that, let me finish. You know, if you're interested in machine learning and AI, I'm one of the editors of the Applied AI letters, and we would love to see your application of machine learning and AI to, you know, chemistry, biology, or any sciences. Open access, no fees. So it's a shameless plug. And with that, let me finish and just, you know, leave you with these links. All our codes on GitHub, you know, plugins for, you know, our neural network many simulation packages, reference data, again, released freely, someone wanna use. And, you know, our neural network used in many academic labs, government institution, NIH, and lots of pharma companies. And thank you very much. And we'll be happy to answer any questions.
Okay, it was very exciting talk. So any questions from audience?
Daisuke, I have a question.
Yes, go ahead.
Very nice talk.
Thank you.
My question has to do with the last part of your talk. And as I understood it, you're using your component with primarily looking at the conformation of the ligand itself, but not the protein ligand energy of interaction. Is that correct?
Sorry, I apologize. I skipped a lot of technical details. The way how it works, you're talking about this, right?
Yeah.
What we do, it's a full simulation. It's, I don't know, 50,000 atoms. So you have protein, ligands, it's explicit water ions, and ligand inside the active site. What we do full system simulation, run molecular dynamics, but this part of the system is described by a neural network, since we already parameterize it to organic molecules. At this point, the rest of everything is still use traditional force field molecular mechanics. But we take into account proteins, environment, ions, all the stuff.
But your intermolecular interaction between the ligand and the protein, is that classical force field?
At this point, we use, you know, standard Coulomb electrostatics and, you know, the Van der Waals at this point, yes. So, but, you know, the point of that errors on the ligand are so big that even fixing this part would give us the better answer.
Yeah, so you're basically removing the scientists from figuring out the force field for every new ligand.
Exactly.
Which is fantastic. But I'm kind of, oh, I see. Okay, but then you just use the normal force field for all of the other intermolecular interactions, which should work fine because you can atom type any of your atoms probably without too much difficulty.
And for many proteins, force field for proteins been tested much more.
Yeah.
There's fewer of them. But every new ligand is a problem because you have this custom.
Exactly. Yes.
Yes.
So the time scale, the time for the calculation is probably still the same as it is for normal MD, for classical MD.
Yes.
Okay. Very nice. Thank you.
Sorry, I had to skip a lot of technical.
No. Yes, of course.
Okay, I see Daipen. Do you have a question?
Yeah, great talk. On a similar note, I have a question. So when you showed the thermodynamic cycle, so for each state, how do we pre-equilibrate the system? Do we pre-equilibrate with the MM and the QM force fields, or do we just
no? We run MD. Yeah, the way how we do it.
Mm-hmm.
You run all the. Again, it's a benchmark paper that may not be accurate. It may not be the most efficient way. But the way how we've done it, you do, for example, everything in force field first.
Mm-hmm.
So you have your force field answer. And then we do, when you have your MM trajectory, we take some window and we take several snapshots which are sufficiently far enough. And you run short this hybrid ML-MM simulations and do some clever reweighting and basically this one is like 10 picosecond, so it's very short simulation of the protein ligand, but you use a neural network for ligand, and basically you compute the correction essentially for the delta G term. So you run like 10 short simulations for every ligand.
Mm-hmm. So in the next layer, it's basically where the QM potential is going to come in, right? Initially,
yeah. So ML here means neural networks have been trained on quantum data.
Right. Mm-hmm. And the other question I had was, so when you do the training and reduce the cost function in the neural networks slide you showed, so how do you, so typically the standard force field, the molecular mechanics force fields are using the Born-Oppenheimer approximation. So is it the same true for?
Mm-hmm.
Okay.
It's the same Born-Oppenheimer. What we do, basically, we take small molecules, molecular, complexes. We run QM and some, quantum mechanical package. We collect energy, forces, and properties. And then we train neural network on energy, forces, and properties, things like charges, if needed.
Thank you.
Okay, I see Brett. You have a question?
Yes.
Oh, hi, Brett.
Hi.
Very nice to see you.
Yeah, great to see you too. Outstanding talk. So, yeah, a follow-up question is sort of about the future. So you showed the really neat simulation of the high temperature carbon gas condensing into these conjugated structures. I wonder, sort of, where is it on your horizon to have a fully reactive? I mean, I know this is reactive in principle, but I doubt you have many transition states in your training data currently for your force field. So yeah, how far out do you think that is to have a quantitatively or semi-quantitative?
I think, version? Since you guys are our friends, we can send you a prototype next month.
Really? You're that confident?
So we have about 100,000 IRC for organic reactions.
I see. And so training against those, you have pretty good coverage of different bond breaking type events.
Yeah. There are no. I'm not saying we solved the issue.
Yeah.
But the, basic reactive potential is very, from what we have right now, internal prototype. We will have it very soon. Then there are a lot of problems because we don't, one of the fundamental limitations what we have right now, we don't have encoding for spin states.
I see.
So then we've done, some tricks, but there is, there are a lot of limitations. So if you're interested in, photo excitation or, all are, or there are metals, you have spin crossing, this is.
I see. But so if you're sticking with sort of neutral organics with just maybe changes in charge state, it's more of just a technical challenge. There's no fundamental challenges. I
think, well, some people would say, no, you basically. But if we are modest enough and let's say 1 to 2 kcal per mole accuracy is enough, if you don't need plus you're okay with describing 99% of normal stuff and don't insist on this 1% of exotic very interesting effect, but then I think it's it's a technical challenge of QM calculations, not the.
All right, thanks. Very nice talk again.
Okay, Tony.
Hi, nice talk. I really enjoyed it.
Thank
so
you.
My question is just very basic kind of background question because I'm not that familiar with deep learning, but can you expand on the idea that what are the limits on the input types of experimental data? For example, you used IC50 as an example, or TM or something like that. But what about, like, let's say more indirectly connected data like phenotypic screens or something like that?
Interesting.
Yeah.
It's all possible, and in industry they use it all the time. When you do phenotypic screen and things like high content imaging, you just need to formulate you just use a slightly different architecture and you train on your images, and maybe yes, those are way high up. You may not necessarily connect to a specific target, but nevertheless you can build this predictive model and kind of to proxy your your phenotypic screens.
Mm-hmm.
And then maybe you can speed up this part. But since you have the gap between the cells and this probably no knowledge about specifically what pathway is involved, then you need to think about how to connect this two.
Yeah. Okay.
So could I ask then, does that actually work? Because phenotypic strings, there's so many variables.
I had very interesting chat over the beer with some GSK folks. They claim it works, but there's no way I can verify that. So, and they will probably not tell me anyway.
Well,
but what I know is they do use very large scale machine learning for internal pipelines for this data.
I think academics need to figure it out and make it public.
Okay, Gaurav, you have a question.
Yeah, hi. So just a comment on last thing. So both for Carol and Tony. So we have some phenotypic screen learning which we have done. We can talk separately what Oles is saying. But Oles, very nice talk. Maybe 1 or 2 questions. One on the first part of your talk, where we were talking about generative models. In the architectures which you have put in, there are certain challenges which come, right, with respect to the chemical space or with respect to generating molecules if you're using graphs up to a certain length. Could you talk a little bit about that? Like what are the kind of current challenges you're facing in that scheme? So specifically
challenges. Great question. Yeah. I think some of these challenges, there's a lot of So I don't think in our formulation, yes, there are some challenges in graph enumeration and matching, graph isomorphism. So those are, yeah, we use some couple of tricks, technical tricks, but I don't think in terms of the length of the graph, it's a problem. What we do right now, since we use what's called the after regressive models, it sort of mimics our distribution of the data. So if you train on, for example, Campbell data, so this is what's a known biologically tested molecules, and Campbell has, let's say, I don't know, 10 to 100 atoms distribution of the length of the molecules. When you train generative model, typically it will mimic this distribution. So you generate from 10, about the same range. So I don't think it's a particularly challenging per se.
So you're
but
not...
the challenge is, you generate, so what, right? I think the challenges are you can generate almost anything. How to synthesize is this challenge.
Right.
And you can generate another billion of molecules. So what?
Right. So in terms of the distribution of your molecules which you get, that is prevalent of the distribution of your training and validation. It's not beyond that. Those things don't work out in that manner.
Yeah, because it makes sense. It's machine learning is not magic, right? What's you in, this is what's you out.
Right. But generative models take into account the distribution of points and changes that distribution, right?
When you do reinforcement learning, yes, it does change.
Right.
That's true. And you change it, you might change it quite dramatically.
Right.
Yeah, please go ahead, sorry.
Yeah. The other thing I was wondering about is, in terms of chemical reactions, there are a lot of data which is out there, which is about only positive reactions. And now combining with your QM, there is almost no negative reaction data out there. So in terms of in terms of combining the QM for those for ascertaining reactivity, do you also incorporate knowledge of conditions like temperature, cofactors and things, or
great. It's a pain point. Yes, we don't know this negative data because it's not published. So I wish we had it.
Yeah,
but the failed examples are notoriously hidden, and the available data is very unreliable. It's very typical. You read a paper and there is 80% success yield. Then the student rerun this reaction and you get 10.
No, but I'm asking that you showed that you are able to make these carbon flakes, which was such a cool simulation. So in that simulation, you incorporate, and whether it's protein simulation or that otherwise, you incorporate the conditions, the temperature. So how do you know what pathways to follow? Because from an entropic standpoint, there are like
that movie was, so that movie is qualitative. So we are not claiming we get kinetics right. This is mostly show off, just to put it there.
Yeah. But I'm just discussing here because
most probably kinetic is screwed because we use relatively low level quantum. There's it's simple reactive potentials. But at least from the point of view of movie and kind of a quick eye of myself as a computational chemist, things look okay-ish. Carbon gets 6 coordinated flakes, things looks how it's supposed to be. We probably screw up all time scales and barriers, and there are a lot of problems with that. But it gets at least the big picture looks okay-ish. But it would be very hard to get barriers and
right. Anyways,
and that we training that potential, the mental data used, unfortunately.
Right. No, I mean that's what it's really cool. It's about figuring out that pathway, whether it's protein simulation or whether it's chemical simulation. I mean, I would love to talk more about reactivity within proteins, but we can meet separately. I'm not taking more time
absolutely.
of the panel. Yeah.
Let's chat.
Yeah, thanks.
Okay. Olexandr, I have a very quick technical question. So for this one, so you have generate, and then you have another neural network, and you connect it by reinforcement learning. You could also connect directly two networks together by the deep learning, just without using reinforcement learning, I guess, and then train it together. Similar to kind of a GAN type of approach, which you have two networks and then you train it simultaneously. What would be the benefit or difference between using this reinforcement learning to connect against the full connected network?
I'll give you my biased answer. GANs are very hard. So in principle, yes, you can come up with scheme, you can use GANs, you can use after-encoded some other methods. It's a mostly preference. In my experience, and with my students, we get discussions. I think we have more success training reinforcement learning. Maybe we have more expertise, I don't know. In our case, what we trained, for example, in this scheme in reinforcement learning was much more successful than we obtained with some of the GANs, because GANs are known to be very unstable. Reinforcement learning is also hard. All of these models are hard to train, but perhaps we were either lucky or have more expertise with RL versus GANs, but none of this model is easy to train.
Sure. Okay. Yeah. Thank you very much. If there is no other question, let's thank to Olexandr again. It was a fantastic talk with various interesting things. Thank you very much.
Thank you so much for the invitation. I really enjoyed the discussion.
All right. Thank you very much.
Yeah.
Yeah. So
Thanks.
yeah,
Thanks
let's keep in touch with people at Purdue, Gaurav, and
yeah. Hopefully next time in person, right?
Yes.
Thank you. Thank you.
Okay. Yeah. Thank you
Thanks.
very much. Thank you. All right. Yeah. Thank you.